So let's talk about cardinality. So the idea of cardinality is the tools you need to ask questions about the size of sets. And maybe we should start with the easiest setting. So there are two sets, A and B. Which of those two sets is bigger? And let's maybe just see a show of hands. Is A the bigger set? Is B the bigger set? Are they exactly the same size? No. Yeah. B is the bigger set. It has 5 things, right? What about those two sets? Is A the bigger set? Is B the bigger set? Or are they the same size? Is A bigger? Is B bigger? Or are they the same size? Yeah, right. So somehow this is an idea that is really easy to understand in the case of sets that are finite. Let's think about sets that are infinite. So somehow, what's the difference between these two sets? Well, one of them you took the exact same set, but you stuck a 0 in it. For those two. Let's compare these two. So let's take all the natural numbers, so the numbers 1, 2, 3, 4, 5, 6, and so on. Compare that with the number 0, 1, 2, 3, 4, 5, 6, and so on. Which of those two sets is bigger? N? N with 0? Are they exactly the same size? All right, so the poll said this one. Those sets are the exact same size. Let's do again. The natural numbers versus only the even natural numbers. So the numbers 1, 2, 3, 4, 5, 6. There's the numbers 2, 4, 6, and so on. Is n bigger? Is just the even numbers the bigger set? Are these two sets the same size? All right, the poll says same size. Indeed, those two sets have the same cardinality. N versus z, so just the positive numbers, or the positive numbers together with 0 and all the negative numbers, so like double the size. Which is bigger, n? I would have been surprised if anyone said n was bigger than z. Is z bigger? Or are they the same size? So you're noticing a pattern. All right, well, what about n as opposed to q? So q is like, an element of q is like given by 2 numbers. So it's like way bigger than twice as big. So maybe q is bigger. Which is bigger, n or q? N? Q? Yeah, they're the same size. What about n cross n? That's like even bigger than q, because an element of q is specified by 2 natural numbers, but like 2 over 2 is the same as 1 over 1, so a bunch of them are really the same. So maybe n over n is bigger. What do you think? Is n over n bigger than n? All right, so you guys are catching on. Yeah, they're the same size. So an interesting construction is the so-called power set. It's the set of all subsets of n. So the set containing 1, 2, 5, 7 is an element of the power set. Which is bigger, the natural numbers or the power set? Is the natural numbers the bigger set? Is the power set the bigger set? Are they the same size? The power set is the bigger of those two sets. And finally, the natural numbers versus R. The real numbers or the natural numbers? Are the natural numbers bigger? Well, they certainly shouldn't be. Every natural number is a real number. Are the real numbers bigger? Are they the same size? So, what is said when someone says the real numbers are uncountable is they are saying that the real numbers are strictly bigger as a set than n is. That's what the uncountability of the real numbers means. But all of that was totally unfair, right? Because one thing I haven't given you is, what does it mean to say that one set is bigger than another set? I haven't given you a definition. So let's give a definition. Definition. For any two sets, x and y. So notice these aren't subsets of anything in particular. So right now I'm doing very abstract, just foundational stuff. I say that the cardinality of x is less than or equal to the cardinality of y, or the cardinality of y is at least as large as the cardinality of x, whatever, if there exists an injective map f from x to y. So, all right, what is that saying? That's saying two sets are the same size is if there's some way of taking each element in a set that's allegedly smaller and generating an element of the set that's allegedly bigger, so that each element of the set that's allegedly bigger is hit at most once. Does that seem reasonable for what smaller should mean? Similarly, well, I'll say the size of y is less than or equal to the size of x if that same statement holds, but x's and y's are flipped, right? It doesn't matter what you call them. And I will say that two sets have the same cardinality. The cardinality of x is equal to the cardinality of y. If one is smaller than or equal to the other, and the other is smaller than or equal to the one. And in reality, that's a theorem. The definition is really something that'll appear, the more standard definition of what it means for two sets to have the same size will appear a little bit later in these notes. So let's go ahead and check some things. You guys told me that, oh, these aren't the right symbols. Let's use the one up here. 1, 2, 3, 4. And I want to use like the example of the top page where they were all the same size. So if A is -2, -1, 0, 1, 2, and B is 1, 2, 3, 4, 0, 1, 2, 3, 4. No, 1, 2, 3, 4, 5. Okay. Those are two sets that you told me at the top of the page had the same size, assuming I've actually written them down correctly, which I feel like I have at this point. Well, oh, it's off the page. Those two sets have the same size. So if you read the definition, two sets having the same size means that the size of one is less than or equal to the size of the other. The size of the other is less than or equal to the size of the one. So that means I need an injective map from one to the other and an injective map from the other to the one. So let's find an injective map from this to that. And they're finite sets, so I can just specify where things go one element at a time. So let's define f from A to B by sending. Well, I guess I have some choices. Where would you like to send -2?
1.
Fair. That's a thing in B, so that's a valid choice. Where would you like to send -1? Where would you like to send 0, 1, and 2? Well, how about 5, 3, and 4? And so now let's just check something a little bit informally. Nope, wrong way. The function that I've just written down, is it one-to-one? Right, so what would you need to check? You would need to say, well, let's consider every pair of elements of the domain. Does that pair of distinct elements go to two different elements in the codomain? And yeah, any two different elements in the domain go to different things in the codomain by inspection. Is it onto? Is every element of the codomain actually hit? I guess it depends on whether it looks like I've still included 0. There, now I've definitely excluded 0. Yeah, so this is a one-to-one function, it's even onto. Oh, the onto didn't matter. So what can we conclude out of this? F is 1-to-1, so the size of A is less than or equal to the size of B. What would we need to do to prove that the size of B is less than or equal to the size of A? Define an injection going the other way. Will that be just as easy? Yeah. Yeah, so how about, well, it was 1, 2, 3, 4, 5, right? Reduce the brightness and turn on the lamp. Maybe that helps. So, let's define G from B to A. Let's see. 1, 2, 3, 4, 5. Those were elements of B, right? Yeah.
Would G equal F inverse?
It could.
Okay.
That function does have an inverse. So let's define G by the formula G of x equals F inverse of x. It's a bijective function, so it has an inverse. So maybe we can even skip all this. Is that automatically an injective function? Yeah, I mean, you could also just check it in this case. And so we make a conclusion. Thus, the size of B is less than or equal to the size of A. So the fact that everything's so easy to do for finite sets kind of says that this theory, well, it takes some work to be rigorous about what one means by a finite set if you're really building the foundations of mathematics from scratch. But I'm going to avoid that. Instead, let's try to do something that's actually surprising. So you guys are, so how many, the poll, I believe, said that the size of the set of natural numbers together with 0 should be bigger than the size of just the natural numbers, right? I think that's what the poll said. I said which the poll said. Like I wrote the word poll somewhere. Yeah. They're the exact same size, though. Let's actually prove it. So, I mean, both of these will be pretty similar. Let's show that the size of n is the same as the size of n union singleton 0. First, yeah. Yeah, the lighting is just so awkward. Maybe what I should start doing is just putting a big piece of white cardboard to keep that from happening, because it's like a lighting level issue, right? Let's show that. Let's show that the size, let's start by showing that the size of n is less than or equal to the size of n union singleton 0. So that means I need to come up with an injective map from the set of natural numbers to the set of natural numbers together with 0. So let's just try to run down. I need a map from n to n union singleton 0. And we have freedom. What is an injective map that takes a natural number and gives me a natural number or 0? N minus 1 will do. Do you think that n plus 1 would also do? Yeah, it would still be injective. I guess you've even found one that's bijective, which is nice. Sure, so let's do that. F of n be given by n minus 1. And one thing that you should always ask yourself is, does this function actually have the right domain and codomain? Can I plug a natural number into that function? For every natural number n, does f of n make sense? For every natural number n, is f of n either a natural number or 0? Yeah, okay, so it actually lines up correctly. So I need to show that this map is injective, so let's consider any m and n in the natural numbers, assume that m is not equal to n, and try to show that f of m is not equal to f of n. Maybe we'll proceed by contradiction? Let's assume, for the sake of contradiction, that f of n is equal to f of m. And we'll try to get a contradiction. So, yeah.
So when we do it for sake of contradiction, do we also still have the assumption that we made previous to the new one that we just came up with?
Mm-hmm.
Okay.
Yeah, so when you're trying to prove something by contradiction, you assume the negation of the conclusion. The conclusion here is that. That's the thing I want to show. So I'll suppose that it's false. If I can get a contradiction, the thing that I was supposed was false must be true. Right, so let's try to do it. Yeah.
When do you have to say without loss of generality?
When do I have to say without loss of generality?
Is it a contradiction proof or like a contrapositive or like, because it's in some contradiction proofs, but like.
Sure. So, if I decided to break this up into cases, one where m is bigger than n and the other one n is bigger than m, I might say without loss of generality. Let's assume that m is bigger than n. What the one without loss of generality means is somehow you're going to say, well, I am going to lose generality, but the proof in the opposite case is the same, or there's like some symmetry argument.
Okay.
Yeah, if like you're just commuting some variables that have the same properties anyway, that's when you might say without loss of generality. But I haven't made any such assumption here. I haven't done anything that might lose generality, so I don't need to say that I'm really not at any point. Okay, so let's try to do it. F of m is equal to f of n. So what does that mean? Well, do I have a formula for f? So I can use that formula, right? What is f of n?
N minus 1 is equal to n minus 1.
Mm-hmm. So
n equals m, which is a contradiction.
this contradicts the assumption that m is not equal to n. Thus, it must be that f of m is not equal to f of n, as we wanted to show. Thus, this function from n to n union singleton 0 is indeed injective, and we conclude that the set of natural numbers is smaller than or equal to the size of the natural numbers union 0. Next, I guess we need to show the opposite. The size of the set containing natural numbers union 0 is less than or equal to n. So I need to define some function that takes a natural number, or maybe 0, and gives me a natural number, and the function better be 1 to 1. What sort of formula would you like to use? G of n equals n plus 1 would do. Would n plus 17 also do? Would 2 times n walk? Well, there's like an issue with 0, right? I need to get a natural number, but 2 times 0 isn't a natural number. So. And then you have to ask yourself, does G actually map n union singleton 0 to the natural numbers? If I take a natural number and add 1 to it, is the result a natural number? If I take 0 and add 1, is the result a natural number? Yeah, it's 1. So, yes. I need to explain why G is injective. And you'll notice that I put that in as a parenthetical. It's something that's worth thinking about, but if the reason is sufficiently obvious, you can just, say it. I need to show that this function is injective. So let's consider any m and n in n union singleton 0, and assume that g of m is equal to g of n. I need to show that m is equal to n. I suppose this time I'm using the other definition of what it means to be injective. Oh, yeah, absolutely. Thank you for pointing it out. So, I don't know, does that look easy to prove too? Gesundheit. Yeah, so let's see. Since g of m equals g of n, what conclusion can we make? And so we can conclude that nice. So this map G is an injective. So n union singleton 0 is smaller than or equal to the size of n. Since I've proven this size comparison holds and that one holds, I conclude that these two sets have the exact same size. How do people feel about that? That argument seem reasonable? Let's do one that maybe feels more complicated by just a little bit. So next I will show that the size of n is the same as the size of z. So I need to show that the size of n is less than or equal to the size of z. And here I'll take advantage of the fact that I only need to find an injective map. So if I give you a natural number and I ask you to give me back an integer, yeah.
Could you explain what injective means?
Yeah! Let's remember what injective means. So if you like, this was like day 1 or day 2 of the class. A function is injective or one-to-one. Or I'll often use like a really sloppy shorthand and say one-to-one. If. And I'll state 2 equivalent formulations. For all x and y in A, if x is not equal to y, then g of x is not equal to g of y. So this is saying if I take any two inputs that are different, the resulting outputs will be different. But this is an if-then, and there are lots of, like that's obviously, I've negated both sides of an if-then, so by the principle of contraposition, that is equivalent to.
I pretty much blocked out this whole weekend so that I could have time to volunteer if I need to. But now that I don't need to have that time, I'm just gonna do this weekend.
So either of those are the definition of what it means to be injective. So, I mean, in principle, you also have this idea of like the horizontal line test is what it means to be injective, but that requires thinking about the graph. If the domain and codomain are like subsets of R, maybe you can. So let's try to come up with one. So I need a map f from z to n, which is injective, and I don't want it written down. But I just need a way of taking a natural number and returning an integer. And, well, what way would you like to do that? If I gave you a natural number and asked for an integer back, what would you do?
Crap. Give me the natural number. When I was at the...
You could give the same thing back.
one of the people who
You couldn't take its inverse, unless you mean like additive inverse. You could take the additive inverse, that's fine. That would give you all the negative integers. You couldn't take the multiplicative inverse, that wouldn't be an integer anymore.
It was just like super helpful.
But when in doubt, like take the simplest thing. So let's just take that natural number and give that same natural number back. Let's take f of n equal to n. Is that definition, is that function like obvious? Well, so cross check. Is that, if n is a natural number, and you read that definition, then is f of n obviously an integer? Yeah, if I take a natural number and I give you that same natural number back, it's also an integer. Is it obviously one-to-one? Yeah. Suppose that f of n is equal to f of m, but that means n is equal to m, which is what is needed. So yeah, that's one-to-one. One thing that I can't do now is that function onto? It does not hit every integer, so I can't just take the inverse. Which is fine. That just means I need to do something else to come up with
the opposite cardinality inequality. So I need to define a map G from Z to the natural numbers, which is 1 to 1. And in order to motivate how we will do this, let's maybe even just think of it this way. So
Up here.
I'm going to try to list the integers one at a time. So maybe I'll do it this way. 0, 1, negative 1, 2, negative 2, 3, negative 3. Do you think I could use that to come up with a way of associating to each one of these a natural number? Yeah, just 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. And so now I'll try to, like, this isn't a proof, but this gives me an idea. So it looks like I'm sending positive numbers to them multiplied by 2. I'm sending 0 and then the negative numbers to, I guess that's multiplied by negative 2 and then add 1. Cool, that gives me a formula. Hopefully it's the same as this formula. Yeah, it's not, but.
I was almost late for class.
Well, shoot, then let's use the one that we just wrote down. So if Z is positive, I will return 2 times Z.
Just judged how long it was going to take to.
If Z is negative, or 0, I will return negative 2 Z plus 1.
And I got to class at 11:59.
And so let's, convince ourselves of some things. So, I claim that any one of these will do the trick. Which one would you guys rather use?
5.
1, 2, or 3? 1, 2, 3. All right, thought we were at. So let's check a few things. So I guess we should convince ourselves at least a little bit that this actually takes every integer and returns a natural number. So there are 3 types of integers. There's positive integers, there's 0, and there's negative integers. If I take a positive integer and multiply it by 2, do I get a natural number? Yeah. If I take, let's deal with 0 on its own. If I take 0, I multiply 0 by negative 2, and then I add 1. Does that give me an integer? If I take a negative number and multiply it by negative 2 and then add 1, does that give me a natural number? Okay, cool. I have the right codomain. So now, I need to show that this map G is injective. So let's consider any 2 things in Z. I'll call them Z and W. Doesn't matter what you call the variables. And assume G of Z is equal to G of W. In order to make sure I don't forget, I'm going to write the formula right here. Yeah.
For integers, that includes 0 as well as positive and negative whole numbers, right?
Yep.
Okay.
Yeah. Yeah, integer includes 0. Natural number is just positive integers, 1 and on.
Okay.
Yeah. So I need to check for injectivity. So that means I get to assume G of Z is equal to G of W, and I want to show Z is equal to W. So I'll break this up into 4 cases. Either they're both already strictly positive, or they're both less than or equal to 0, or one of them is strictly positive and the other one is less than or equal to 0, or one of them is less than or equal to 0 and the other one is strictly positive. So certainly in those last 2 cases, I could say without loss of generality, let W be the one that's strictly positive and eliminate one of those 2 last cases. Instead, I've taken the strategy, this one of, taking no strategy, just doing it again. All right, so let's just check. So in case 1, I have a formula for G of Z it transforms the assumed equality g of z equals g of w into, I guess, 2z equals 2w? Because that's what g is when z is bigger than 0? All right, well, if 2z is equal to 2w, then you can conclude that what did you do to get that?
Divide by 2.
Very good. In case 2, I'm not even going to bother doing it because it's the exact same thing except you add 1 and then divide by -2, I guess. So I'll jump to case 3. In case 3, which, just for the sake of emphasis, was that case, let's write it down. In case 3, I have z is positive, so I get 2z equals g of w is less than or equal to 0, negative 2w plus 1. This is a contradiction, I claim, because well, I guess, let's even just try to do this. Because that will mean, I guess, that 2 times z plus w equals 1. But is 2 times z plus w ever equal to 1? Yeah, right? One of those numbers is even, the other one is odd. I guess here I'm assuming basic facts like 1 is not even. But 1 is odd, while 2 times z plus w is even. Do you think in the opposite case where z and w are switched, it'll be like a pretty similar argument?
Yeah.
So I think I won't even bother saying it. Thus, this map G is injective. I conclude that the size of the set of integers is less than or equal to the size of the set of natural numbers. And so these two sets have the same size. Everyone feel pretty good? These proofs feel all right? So the next thing that I want to state is a few abstract properties of cardinality. And maybe we'll give some ideas of some of these. Or maybe we won't. So the first is the cardinality of A is the same as the cardinality of A. So that's like, just like is this well defined? I guess in terms of an equivalence relation, this is checking if this relation is actually symmetric. So to do that, all you need to do is, given any set, come up with an injective map from that set to itself. Do you think you could probably do that? If I give you an element A in A, how would you give me an element of A? You could just give me A back. Right? So you could probably use G of A equals A. So that would show that the size of A is less than or equal to the size of A. Oh, but wait, that means the size of A is less than or equal to the size of A. So the size of A is equal to A. So that's what it means for two sets to have the same size. If the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of C, then the size of A is less than or equal to the size of C. So there's a transitivity property. And if you like, all this is saying is if you compose injective functions, you get an injective function. How many people have seen the proof of that? Composition of injective functions is injective? Okay, then maybe I'll add a little bit more associated to the whole. And if that is true for inequality, because equality is defined in terms of that, you get the same for equality. The next one gives a reformulation of what less than or equal to means. So maybe instead of saying this set is less than or equal to that set, if I can fit this set inside of that set via an injective map, maybe I'll say this set is bigger than that set if I can take this set and crush it down so it covers all of that set. So what this result 4 says is, assuming you have non-empty sets, then I will say that the size of A is less than or equal to the size of B, if and only if there is a surjection from B onto A. And finally, the Cantor-Schroeder-Bornstein theorem says that if you have two sets, then they're the same size, if and only if there's a bijection from B to A. And you'll notice there, like, I've been using like a hook at the end to indicate injection and a double arrow to indicate surjection. So something that's an injection and a surjection will have a hook and a double arrow. That's not a standard convention, but I think it's a meaningful one. And this will be a challenge problem, which you can see a short description of in the homework section. So let's just say a few things. So claim 1 is let f of A be equal to A, show that that's injective. Proof of 2 is show that a composition of injective functions is injective. Theory is basically just look at 2 and use 2 twice. The proof of 4, I'll say a few words about right now. So it says here that like the idea is that this is like trying to invert an injective function to get a surjective one. And there is detail in this document about that, but instead I'll just give you like the cartoon picture. So there's an example of an injective function, the graph of one anyway. I can invert that function, and I'll get a surjection from a subset of R2R, but that doesn't have the right domain. So what do? I fix it by taking all the things that aren't in the domain and saying, well, I already hit everything, so I don't care where anything else goes. I'll just send all of those things to like 5. And that's exactly what I'll do. That's what this formula says. If I have an injective map, then I will define G from B to A by either taking the rule that gives you the inverse function. I will set G of B equal to A whenever B is equal to f of A. And I will just pick some element of the domain A0 and define G of B to be A0 all other times. And you have to prove that that's surjective. Well, first you have to prove that it's actually a function. That takes some work. Not much. Using that as injective. So I'm not going to go through the proof, but how do people feel? Like that seems like something that could be done? I want to show G is surjective. Oh, well wait, if I just told you I had to tell you what injective means, do you want to remind her of what it means to be surjective? Yeah, that should mean that like everything in the codomain is actually in the range. It's a y line, so it should be a y. A function is onto it for everything in the codomain. Yeah.
And what's the codomain again?
The codomain is, so it's the place where you know that all of the values live. You don't know that every one of those outputs is hit. Yeah.
What's the little dot in front of the A?
Oh, that's supposed to be a bullet point.
Okay.
Like I wanted to,
Okay.
there were bullet points there, so I wanted to put a bullet point there, even though there weren't any ors.
Okay.
That's the only definition. So if you wanted to prove that claim, then you would have to prove that this function is onto. But then there's the opposite claim. If there exists a surjection from B to A, then there should exist an injection from A to B. And I'll do the same thing. I'll motivate some definition by a picture. There is a surjective function that is not onto. Right? Every y value is hit. And so what will I do? Well, I want to motivate this by like taking the inverse function. So I take the inverse function, except is that actually a function? No. So what will I do? I'll make it a function by just erasing enough to make it a function. So The stuff that's dotted is not actually part of the graph. And well, now let's just check. Is that graph the graph of a one-to-one function? Yeah, it passes the vertical line test, so it's a function. And it passes the horizontal line test, so it's a one-to-one function. Now, do whatever it is you do by exactly that. So what will I do? Well, for every element of A, I know that the pre-image of A is for everything in the thing that's being surjected onto, there's something in the pre-image. Just pick one of those somethings. Define F by just using that something. So right here, it looks like I had a choice of 3 different things to be F of that number. Just pick one. I don't care which one. Just pick one. And if you like, this is using the axiom of choice because I'm picking something. So that's one of the axioms of set theory that makes studying foundations of mathematics challenging. How do people feel about that argument? That seem okay? It was very fast and a little bit informal, but do you believe the result? And as I said, the last one, well, one of the things is straightforward. If I know that there's a bijection between two sets, then there's certainly an injection going one way and an injection going the other way by taking its inverse. So one implication is obvious. The other one is less obvious. If I have an injection going that way and an injection going that way, they don't have to line up to be inverses. So you have to come up with some sort of trick. And a challenge problem says, well, look up the proof of the Cantor-Schroeder-Bornstein theorem and come present it to me. So finally, with not enough time, let's start explaining. Okay, so it looks like we'll be doing more of this next time. This is the first time I've done this particular note packet, so I'm not terribly surprised that I screwed up the timing. I'll go ahead and tell you what the homework is. So the homework was just to prove 2 of those claims. And so I think I feel okay about that homework still being assigned. So let's prove these, as much of these as we can. Let's prove that the size of n is less than or equal to the size of n cross n, and the size of n is equal to the size of q. Oh, yeah.
Thank you.
So let's start with this. So I need to come up with a function from n to q. Well, if I give you a natural number and I ask you to give me a rational number, what would you want to do? Yeah, just give me the same number back. Every natural number is a rational number. And I'm going to go ahead and say yes, it is obvious that that is injective. Next, I need to show that the size of... nope, that's what I've just done. I will choose to next check that the size of q is less than or equal to the size of n cross n. And here's how I'll do it. What is a rational number? Well, a rational number has something of the form p over q. But you can always assume that q is a natural number. Right? The denominator can always be arranged to be non-negative, to be positive even. You can't divide by 0. And that it's in reduced form, meaning that p and q have no common factors. I will now define g of p over q by the rule 2p plus 1, comma q, if p is bigger than or equal to 0, negative 2p, comma q, if p is less than 0. So basically the only thing I'm saying is, well, if the numerator is negative, make it positive. But then to prevent 2 numbers from going to the same number, well, multiply one of them by 2 and make the other one odd. So maybe I'll ask 2 things. Is that obviously a function? Yeah. It's a way of turning inputs to outputs. Does it obviously take values in n cross n? Yeah, the only things that can be negative, when they're negative, I multiply by -1 and add 1, so they become positive. And next we need to check that it's 1-to-1. And maybe that's less obvious.
What do you think? You think you can give that function as 1 for 1? Consider any two things that look like P1 over Q1, P2 over Q2. What do you think? Case-wise analysis? Ooh. So I've eaten up my time. What we'll start in on Monday is we'll finish proving this surprising fact, right? Q should be bigger than N. We'll prove that it indeed isn't. And then we'll prove the other surprising thing, well, if all of those sets were the same size, there does actually exist a set that's bigger than N. Namely the power set.
So would we prove that the same way that we just proved